All right, the mass of a handful of copper coins is 144 grams. The coins are at a temperature of 33 degrees C. Grams of pennies, and it's 33 degrees C. And then what we're going to do is we're going to lose minus 1.47 kilojoules when they are tested in a fountain, tossed in a fountain, and dropped into a fountain. What is that? What is that temperature? So what they're asking for is the final temperature here. And so if the fountain's final temperature were negative, then it would be frozen, usually. I mean, it depends on how much salt is in there. It is possible it could go negative and still not be frozen if there's a lot of salt dissolved from, what's that called? Colligative property. Well, colligative property. Freezing point depression. But freezing point depression doesn't depress it terribly much. And so what they're doing here is, okay, then it's going to reach some kind of temperature. The coins didn't undergo phase change. So this is just object cooling. It's going to be MC delta T. So is that pretty much what you did? Mm-hmm. All right. And so if we do this, we can plug in minus 1.47 kilojoules here. Because when they say it's lost, then we have to put the negative sign. If it's gained, then we'll put the positive sign here. But normally energy is positive. This is just include the negative. The mass is going to be 144 grams. The situation is, what is the specific heat of these? Well, they don't say these are pennies. Because pennies are not pure copper. Pennies are 2.5% copper, 97.5% zinc. So if that's the case, then we have to treat these separately. This would be a more advanced problem, where this would be maybe a Chem 1A cell problem, where you figure out how much heat for the copper, how much heat for the zinc, and then come to the same final temperature. But in this case, this is just going to be pure copper here. So what was the specific heat of the copper?
0.38 joules per gram degree C.
And then you did a delta T? Or did you solve for delta T final?
I solved for delta T.
You solved for delta T? You did solve for delta T here. What did you get for your delta T?
I got 26.864.
Negative?
That's what I was confused about, because it's dropping temperature, so then it should be, that would be positive, or?
Oh, well, if it's dropping temperature, it would be negative. Yeah. And also, keeping track of the sign here, what we eventually have to do for all these equations is keep track of the sign. And so if they said heat was lost, we have to put the negative sign there, otherwise the math is not going to come out correct. Or if they say it's heat's gained, then we have to put the positive sign there. And in all the calculations, we're going to have to do that. We're going to have to keep track of the sign afterwards. And so in this case, it's going to be negative 26.864, and that's going to equal T final minus T initial. And they give us T initial is 33 degrees, so T initial is actually quite warm, 33 degrees C. And then we'll calculate T final here. T final is going to be, we'll just add T initial to both sides, so that's going to be 33 degrees C minus 26.864 degrees C. I'll just say 26.9. It will give us 6.1 degrees C. Is that what they got? Mm-hmm. Yeah. This is going to be positive 6.1 degrees C because that's going to be the final temperature of the coins and the fountain. So the coins are going to come out to the same temperature as the fountain.
And then would it be only one significant figure?
Yeah, because you're right. This is 33, so we go to 6 degrees C. Okay, you said there are other questions as well?
I had another homework question for chapter 16.
Chapter 16.
Number 134. Oh yeah, this one I was just confused about how the freezing point and the boiling point are like correlated.
Okay. You said it was number 34?
134.
134. All right. Antifreeze is put into the water in an automobile to prevent it from freezing in winter. What does the antifreeze do to the boiling point, if anything? Whenever you have a solution, two things happen that you need to know for this. So if you have a pure liquid, it's going to have the boiling point of the pure liquid plus the freezing point of the pure liquid. And we can characterize it like water. Water's boiling point is 100 degrees C. Its freezing point is 0 degrees C. But if you add solute to this and make a solution, then the solution is not going to have the same boiling point. The boiling point of the solution is going to be greater than the boiling point of the pure liquid. And the freezing point of the solution is going to be lower than the freezing point of the liquid. So if we have salt water boils at greater than 100 degrees C and freezes at less than 0 degrees C, salt water. Ethylene glycol is this. You know, if the boiling point is higher, then we call that a coolant. You know, this is for antifreeze. So in the summertime, the antifreeze acts as a coolant because the water can stay liquid at temperatures higher than 100 degrees C. So it helps cool the engine. And so we use ethylene glycol as a coolant. And so that's why in the summer, we want to put this in here because that's going to help cool the engine down. Now, antifreeze is ethylene glycol. Ethylene glycol is very water-like. This is an ethylene group, and the glycol part is two alcohols stuff. So we have an ethylene sandwiched in between two alcohols. And so this can hydrogen bond quite well with water. In fact, this is miscible in water. And so what you can do is you can get high concentrations of antifreeze in there. The higher the concentration, the more the boiling point is increased and the lower the freezing point is. So in the summertime, it doesn't boil over. The antifreeze, coolant here, and then antifreeze here. And so they say it's an antifreeze, but it's actually does two things. It's a coolant in the summer, and it's an antifreeze in the winter. So you don't want your coolant to freeze during the winter, and so you add lots of ethylene glycol. Some people just add water. They do this to like windshield washing fluid. Some people just put straight water in there and it freezes over the winter. Actually, that's what they did here. I had my car, I ran out of antifreeze. I had my car maintenance, and they just put water in there. And I said, oh, I'm going up to the snow. And so I asked them to put some actual windshield washer fluid rather than water in there. And so we did that. But it does two things. So the question is, this one, it's antifreeze / coolant is what you buy, and that Xerox is antifreeze / coolant. Does that make sense?
Mm-hmm.
So that's what they're talking about. And both are going to happen regardless. Okay, other questions?
I have one other question. This one's kind of more general, but like, there's a lot of questions on, I forget what chapter it is. I think it's chapter 13 homework, and also on one of the practice exams we use, where they just ask like, what's the bond angle? So for that, no matter what even if the like electron geometry and the molecular geometry are different, will the bond angle always be the same?
For Chem 4, yeah, it'll always be the same. In Chem 1A, you might want to know the difference. And so for Chem 4, that's why we'll label it the ideal angle. And so when you have, let's go to trigonal planar state. This is just atom A. Trigonal planar. And so the electron geometry and the molecular geometry are both trigonal planar. And then the angle is going to be 120 degrees and 120 degrees. However, if we have a lone pair there, the electron geometry is still going to be trigonal planar, but this is going to be bent, the molecular geometry. We have two bonds and one lone pair. If it's trigonal planar here, it's going to be 120 degrees. And for the bent, it's going to be 120 degrees. This is the ideal. But there's normally about a 2-degree distortion. So it's going to be a 2-degree distortion here, 2 degrees distortion, like a 4-degree distortion here. And so maybe about 116 degrees distorted. And so in this particular case, when we have a different molecular geometry, it's going to result in distortions. And it depends if you want to keep track of those distortions or not. And so the angle they're probably going to ask for is just the ideal angle, 120 degrees. But these distortions, this is just a guesstimate. It's not necessarily accurate. And so the same thing with tetrahedral. I mean, if we have tetrahedral, if it's tetrahedral for the EG and the MG, then it's going to be 109, 109. But if we go to trigonal pyramidal, it's going to be 109, be the tetrahedral ideal angle. But when we look at the molecular geometry, trigonal pyramidal, we don't necessarily expect a 109 angle here. We expect about a 107 angle. And then if we have two lone pairs, maybe I'll put those lone pairs. Then we'd expect a bend at 105 degrees. So I don't know. Did they not do this in chapter 13? The distorted angles? No. They just did the ideal. All right, then you just need to worry about the ideal angles for now.
Can I go on the test?
On the test, I'll just ask you, what is the ideal angle? I don't know if how about that last test? I don't know if I asked you any distorted angles. Let me take a look at that last This is an exam 3.
I think it was in the first, exam 3. Well, that is the predicted bond angle on the dioxide.
Yeah, I didn't make it clear, did I? What is the predicted bond angle? And so that's not clear. With CO2, there's no distortion. So what is the bond angle in CO2? 180. What is the predicted bond angle in H2O? Okay, here I didn't do any, because these are ideal, 180, 120, 109, 90. Actually, this is 109 or 109.48 or 109.5. And so in this case, the closest one would be 109. What is the predicted bond angle in SO2? SO2 is like this here. And so here it would be 120. Yeah, so these are just ideal. The answers for this are wrong. It's supposed to be like this. And so I talked about the distortions. Because in Chem 1A, you're expected to know. In Chem 1A, they say less than 109. The angle is less than 109. But less than 109 is anything from 0 to 109. And so you try to pinpoint it a little bit more rather than just saying less than 109. That's what they do in the Chem 1A book. But again, sometimes it's hard to predict because it depends on how big the central atom is. Sometimes the central atom is big, so that these valence shell electron pair repulsions aren't so significant, and so the distortions, the angles aren't so big. So it varies. But as long as you're aware that it could be distorted, you're fine. And so just do the ideal.
Are you going to be giving the distorted angle as one of the answers? I know you're saying that now that you can do ideal, but I'm just curious because on the midterm there was a few questions that you had put that the answers were kind of difficult to sift through. So I'm just curious. It's fine again.
No, I'm actually no.
I just would be really confusing.
Right. Right, because you'd be debating, am I talking about the ideal or the distorted? And so that's why I put it in here. What is the predicted, what is the ideal bond angle? Well, ideal could be the distorted, you know. So anyway, since we don't talk about it, at least they don't talk about it in the book, we'll just go with these. These are the game. This question, some of these questions came from the book, so I just used the answers as is. But the cause of the distortion is this. You know, when you have a bond, it's a tug of war between two atoms. So atom A is pulling the electron cloud, atom B is pulling the electron cloud. And if that's the case, then that electron cloud is spread out, you know, between atom A and atom B. But when you have a lone pair, there's no tug of war. Only atom A is pulling it. And so if atom A pulls all the electron cloud towards it, the electron cloud is very intense right here, which leads to greater repulsions. So lone pairs require more space because the electron cloud is a bit more concentrated, and that results in the distortions here. We see.
Let's go over what is the shape of NH3.
Okay, do that. What is the shape of NH3?
Trigonal pyramidal.
Yeah, trigonal pyramidal. Because when we do the Lewis structure for NH3, it looks like this. Nitrogen with one lone pair, 3 bonds. So the electron geometry is going to be tetrahedral, but the molecular geometry is just going to be trigonal pyramidal. So that's the answer to 35. Is that enough?
Yeah. I just wanted to go over the true and false questions in chapter 15. I noticed some of them were.
Okay. True and false questions in chapter 15.
Mm-hmm.
I don't want to What were the true and false questions at the beginning of the or the end?
100.
So it's just structure. It's not. Cool. Because I was like polarity. I think it's like.
All right. Classify each of the following statements as true or false. A. Intermolecular attractions are stronger in liquids than in gases. Is that true or false? Intermolecular attractions are stronger in liquids than in gases. This can be true. We have to assume it's at the same temperature. And so what holds liquid particles together? The intermolecular attractions are much more stickier if it's a liquid at room temperature versus if it's a gas at room temperature. So water is much more stickier than ammonia. Ammonia is a gas at room temperature. Water is a liquid. And so the intermolecular attractions are stronger. Ammonia can liquefy. It's easy to liquefy ammonia compared to something like CO2 or O2. Those are much harder to liquefy. B. Substances with weak intermolecular attractions generally have low vapor pressure. False. That's false. If they have weak intermolecular attractions, then it's easy to vaporize. If it's easy to vaporize, then they should have high vapor pressure. C. Liquids with high molar heats of vaporization usually are more viscous than liquids with low molar heats of vaporization.
True.
That's true. You know, high molar heat of vaporization means it needs lots of heat to vaporize. If it needs lots of heat to vaporize, that means they're really sticky. If they're really sticky, then they're going to be more viscous. resistant to flow. D, a substance with a relatively high surface tension usually has a very low boiling point. A high surface tension means the molecules are hard to break apart from the surface. If the molecules are hard to break apart on the surface, then the boiling point should be high. Yeah, that's false. All other things being equal, hydrogen bonds are weaker than induced dipole or dipole forces.
False.
This can be a trick question here. This is why they said all other things being equal. Yeah, usually in Chem 1A they say for small molecules. For small molecules, hydrogen bonds are strongest, you know. But when you get to large molecules, then the induced dipoles can be quite tremendous because of the large number of electrons in the electron column. And so this one can be argued either way, you know. But the correct answer for this particular one is all other things being equal, hydrogen bonds are stronger. And so this is false. Hydrogen bonds are stronger because they result in unusually large dipoles, which are typically bigger than induced dipole and dipole force. Dipole forces is normal dipoles. Induced dipoles are usually the weakest unless you have a huge electron cloud. If you have a huge electron cloud, then these can be the strongest induced dipole. So for example, if we compare asphalt, you know, asphalt is oil, you know, molecules that are held together by induced dipole forces. With water, water is a liquid at room temperature, and that's held together with hydrogen bonds. But asphalt's a solid, and they use that to pave roads.
So wait, that would be induced dipole?
Induced dipole, yeah. Asphalt, it just has gigantic hydrocarbon molecules in the asphalt. Asphalt also
is an oil.
Asphalt, also known as bitumen, is a sticky, black, highly viscous liquid or semi-solid form of petroleum. Petroleum is a hydrocarbon mixture. It may be found in natural deposits or may be refined. And so this is asphalt here. It's held together by induced dipole forces.
I remember going to the Brea tar pits.
Oh,
And
yeah.
just outside it, there's just so much hydrocarbon deposits, even like in the like park area. You
Yeah.
could see it coming up.
Yeah. Yeah. The beaches around here don't have this problem, but you know, when I was young, all the beaches in Santa Barbara had tar all over them, and so when you go home, your feet are black from the tar. And so I remember my mom taking gasoline and then using gasoline to get the tar off the bottom of my feet. I hated the smell of gasoline. You know, it smelled awful, and that was leaded gasoline back in high school. No, I wouldn't want to do that to any children.
I mean, did the tar burn?
No, the tar didn't burn. It's just sticky. It doesn't come off the bottom of your feet. And so, but you know, there are a lot, like acetone would work well. And a lot less, you know, hazardous things that you could have used. You know, probably acetone would have been best.
Maybe say some of the Santa Barbara beaches can like injure your feet. I don't know what's out there.
Don't let children out on beaches with like tar on it and stuff?
Yeah, there's a whole bunch of tar because of all the oil there, and then there's natural seepage. You know, there's Coal Oil Point, which has lots of tar just all over. And then you could be careful where you step. You know, try to avoid blotches of tar, but after a while, it just becomes a hassle. There's so much. And I don't know how much there is now, because they're doing a lot.
I have a question on the specific heats.
Mhm.
Are you going to give those in the question?
Yeah, either it's given or you calculate it, you know. As we could calculate the specific heat if we're given Q, M, and delta T. If we're given Q, M, and delta T, then we would calculate C. So sometimes you calculate what the specific heat is.
It seemed like in the homework they were just kind of telling you just go check the.
Yeah, or the table. This is given in the table.
Are you gonna give us the table or?
I'm going to give you the specific heat if I am going to ask you a specific heat question. Let me take a look at what I did on the last exam. I don't think I had a specific heat one here. I think there was one question here. Calculate the heat required to convert 25.2 grams of ice at minus 5.0 degrees C to steam at 105 degrees C. So I gave you the specific heat. Specific heats of ice, 2.06 joules per gram degree C, water, 4.18 joules per gram degree C, and steam at 2.00. This one, number 45, this is a lot of calculations. How many steps are there? Well, the first thing is you have to warm up the ice. So that's calculation one. Warm up the ice from minus 5 to 0. And then we have to melt the ice. Heat of fusion. Then we have to warm up the water to 100 degrees C using the specific heat. And then we have to boil the water or vaporize it at 100 degrees C. And then we have to heat it to steam. So this is a lot of calculation. On your test, this will be a multiple choice question, so it'll be like one or maybe 2 steps at the most. It's not going to be like 6 steps. And so you'll be given the specific heat in the problem. So let me see if I give another problem. No, I didn't. Yeah, you don't have to have any specific heats memorized. Some people have water specific heat memorized in calories. It's 1 calorie per gram degree C. 1 calorie is the same as 4.18 joules. So this is 1 calorie per gram. Because of water, it's because water. It was defined based on water, the calories. The joule is how much, 1 joule of energy is the amount of energy required to lift 1 kilogram mass by meter. But a calorie is defined as the amount of energy required to heat 1 gram of water by degrees C. That's what I count. We can take a look at some of these. I'm going to look at exam 4. Take a look and see what types of questions are. Let me finish the true false here. The essential feature of a dynamic equilibrium is that the rates of opposing changes are equal. Is that true or false? Well, it's true. The dynamic part of this is that the rates of opposing changes are equal. Since the rates of opposing changes are equal, that's the equilibrium part because nothing changes, overall. Although there's constant change because, for example, in vaporization, you always have vaporization and condensation happening.
I thought that was the central feature, was that it's constant. substance is in constant.
Well, yeah, it's in constant change, but it's going in circles because if one was bigger than the other, then there'd be a net change. Let's say net vaporization or net condensation or net dissolution or net precipitation. But since it's at equilibrium, there can't be any net change. Equilibrium vapor pressure depends on the concentration of vapor above its own liquid. That's true. The higher the concentration, the higher the pressure. We call that volatile. The more volatile it is, the more molecules, the higher the concentration. The heat of vaporization is equal to the heat of fusion, but with opposite sign. Oh, that's false. The heat of vaporization is equal to the heat of, heat of vaporization, usually. But the heat of condensation is usually equal to the heat of vaporization, but with opposite sign. And so we could say the heat of vaporization is equal to the heat of condensation, but with opposite sign. Or the heat of fusion is equal to the heat of freezing, but with opposite sign. You just have to change the sign of one.
So the heat of vaporization is equal to what again?
Heat of vaporization. In the table, they only give us heat of vaporization. If you want heat of condensation, then you just change the sign. Heat of vaporization, since it's the first process. They don't give us heat of fusion, but if you want heat of freezing, we just change the sign. And so the heat of vaporization of water is 2.26 kilojoules per gram. And so the heat of condensation would be negative 2.26 kilojoules per gram. The heat of fusion is 333 joules per gram. The heat of freezing would be minus 333 joules per gram. The boiling point of the liquid is a fixed property of that liquid, the liquid. Is it true?
I feel like it could be true, but also doesn't it depend on like the pressure?
Yeah, it does depend on the pressure, but in a fixed manner or in a variable manner?
Fixed.
Yeah. And so the boiling point of liquid is a fixed property of the liquid, and that could include the trend in boiling point versus the pressure. And so what would be fixed is this curve. The curve would be the vapor pressure curve of water. If we look at the vapor pressure curve of water, then we have at 1 atmosphere, we have the normal boiling point here. But we can determine the boiling point at any other. Like, for example, at higher pressures, the boiling point increases. At lower pressure, the boiling point decreases. And so this curve, the vapor pressure curve, would be a fixed property of water, where we can predict what the boiling point should be based on the pressure. And so in that sense. But I see your point. You could argue it the other way too. You could say, well, it's not fixed. The number's not fixed because the pressure can change it. But it changes it in a very well-defined way here. If you break an amorphous solid, shatter amorphous solid, it will break in straight lines. But if you break a crystalline solid, it will break in curved lines. That's false. The opposite. And ionic crystals are seldom soluble in water. That's false. Ionic crystals are typically soluble in water unless the ionic bonds are too strong. If the ionic bonds are too strong, then it's insoluble. But that's one of the properties of water. You know, in biochemistry, this is one of the most important properties of water, and that's its ability to dissolve things like salts, electrolytes, gases. And molecular crystals are nearly always soluble in water. Maybe nearly always. I would say that is true or false.
False.
I'd say that's false because although there are a lot of molecular solids, crystals, that are soluble in water, there are a lot that aren't, like wax. What else? You probably can think of a bunch. And sulfur. But then you can probably think of a bunch that are soluble. So I probably avoid this question. Oh, the numerical value of heat of vaporization is always larger than the numerical value of heat of condensation. Is that true or false?
False.
That's false. They're equal and opposite. Sorry. So if you were to vaporize a gram of H2O liquid at 100 degrees C, to get H2O gas, 1 gram at 100 degrees C, this is going to cost you 2 kilojoules. 2 point whatever it was. Can't remember. .26 kilojoules per gram. So to take H2O liquid at 100 and convert that into H2O gas at 100, it's higher energy. This is energy here. And so steam is a higher energy, even though it's at the same temperature as water. They're at the same temperature, so the kinetic energy is the same. The potential energy is different, though. And so steam has higher potential energy. We have to lose that potential energy to condense it, so it's going to cost you the same amount. And so condensation is minus 2.26. Vaporization is plus 1.26. And so numerical value is the same, just opposite. So heat, the units of heat of fusion are kilojoules per gram degree C. Is that true or false?
That's false.
That's false. It's kilojoules per gram. There's no degree C because the heat of fusion, there's no temperature change. When we melt ice, the temperature stays at 0 degrees C, and we end up with liquid water at 0 degrees C. So whenever there's a change in phase, the temperature never changes. Here, there's no delta T here. When we vaporize water, the temperature stays the same. When we melt ice, the temperature stays the same. And so there is no degree C part to it. This is going to be kilojoules or joules per gram. Q, the temperature of water drops while it is freezing. That's false. The temperature stays the same, 0 degrees C, until it's all frozen. R, specific heat is concerned with the change in temperature. Yeah, specific heat, the focus of specific heat is change in temperature. Objects cooling, objects warming, that's specific heat. And so that gives us the Q is equal to MC delta T equation. So the specific heat is always concerned with how how things change temperature. So things with low specific heat like copper versus things with high specific heat like water will have dramatically different temperature changes with added energy or removed energy.
Going back to the units of heat of fusion or kilojoules over grams, that should be changed to joules over grams, or could it stay as?
No, it stands still.
Okay.
The heat of fusion in the book is in joules per gram, but it doesn't matter. Kilojoules, joules. This is 0.333 kilojoules per gram. Okay, were there other questions from the homework?
Can you go over 60 real quick
60.
on the same chapter?
It's
That one didn't have a solution.
All right, types of crystalline solid. The physical properties of four solids are tabulated below. In each case, state whether the solid is most likely to be ionic, molecular, metallic, or covalent network. So, number 60. The melting point, is that high or low? The melting point? It's low. If it's low, you have two choices. It's either molecular or metallic. Some metallic solids have very low melting point. But we know that its conductivity, it's a non-conductor, so it can't be metallic. It's got to be molecular. A molecular can be water soluble or insoluble, so we don't have a clue there. But this has got to be non-polar molecular. Non-polar molecular because it's insoluble in water, it's a non-conductor, and it has a low melting point.
So if we were to say molecular solid, that's not enough to be.
No, you molecular solids are not.
Oh, okay.
D, this is a very high melting point. And it's an excellent conductor of electricity, so this has got to be a metallic. And so metals have wide-ranging melting points. So metals aren't soluble in water. Metallic.
Yeah, where I got confused was like, the book has it described, like for instance, 59. Calls it a network solid, but
Which one? A?
yeah, like I got confused between the covalent network solid and just a network solid.
Same thing.
Okay.
Covalent network and network solid are same. And so it's 2000 degrees C. This one, you're guessing here. Because this could potentially be ionic, just with very strong ionic bonds. And so this is just a guess. It's either ionic or network. B, it's soluble in water, so this has got to be ionic. It's very high melting point. I don't think I gave any questions on the test like these. We can take a look at the test. Were there other questions? All right. How about this? Did anybody do this? Want to wait? We were talking about this, or talk about this now? Wait. All right. Yeah, we'll wait.
For I think it was chapter 16. There was a question where like H2O equals, the grams of H2O equals to the milliliters of H2O. I didn't understand that.
That's not something we always do. So for example, 1 gram of H2O is 1 milliliter, about, because the density is about 1 gram per milliliter. And so whenever we say, if I had 1,000 grams of H2O, I just say that's 1,000 milliliters. It's close enough. It's not exactly 1,000, but it's close enough. So that's what they do.
Okay.
So anytime you see grams of H2O, then you use them interchangeably, milliliters and grams.
That's only for H2O?
That's only for H2O, right? But if you want more precision, then you have to calculate it because the density is actually a little less. It depends on where you are in this. For example, here. Um, You can see the density changes. The density is only 1. This is in kilograms per cubic meter. This would be 1 gram per milliliter. The density is only about 1 at 4 degrees C. But, it doesn't change that much. I mean, if you look, if we're at 10 degrees C here, it's gone to 0.9997, around there. 99, a little bit higher than that. And so, it depends on how precise we need to be. If you need to be super precise, then you're going to get the density of water at that temperature and then calculate what the volume is rather than just assuming it's around 1. The calorie is defined here. The calorie is the amount of energy required to heat water from, I think, 4 to 5 or 4.5 to 5.5, something like that in this region, or maybe 3.5 to where it's most dense. The specific heat changes a little bit, it becomes less dense here, but not enough to worry about. Okay, other questions?
So going into saltwater and freshwater, where overall saltwater in an ocean is a mixture.
Yes.
But if you take a sample of that, would that be homogeneous or?
Ocean water?
Yeah, that's where I was like trying to understand.
It's yes and no. I mean, it depends on what level you look at it. If you can look and you see plankton in the water or you see debris in the water, then it'd be heterogeneous. If you don't see anything, then it's homogeneous. So it could be argued either way, it's homogeneous or heterogeneous. And so, you know, I mean, like if you look at brass looks homogeneous. But if you look at brass using a powerful microscope, things start to look heterogeneous. It depends on what level you look at it. And so the naked eye it looks homogeneous, but once you start looking at it close with a microscope, it's not. it's not homogeneous anymore. And so, and this is hard to see. Don't worry about it.
Okay, yeah, because I think it was in the intro for,
What did you call it? Homogeneous
let's talk about ocean water.
Yeah, in this edition, I don't think I have that. Okay.
Yeah, if I can find it, I'll let you know. But,
All solutions are homogeneous. It's supposed to be homogeneous.
yeah, it says here, any well-mixed individual sample of ocean water is a solution.
Okay, then it will be homogeneous.
Yeah, and that's where I was like, what?
No, but there's a lot of kelp. Santa Barbara has a lot of kelp in water. And you have little tiny particles of broken up kelp in water. So when you grab a sample of water, there's a whole bunch of stuff floating. I think here.
I guess it's talking about like if you stir or agitate it a lot, then you'll get a homogeneous solution. But will you give us the boiling points for different things?
Yeah.
Okay.
You don't have to have any of that kind of stuff memorized. All right, let me talk about lab for tomorrow. So we're going to go back into lab, and if you didn't do the ammonium test, this is pretty straightforward. I talked about the ammonium test already. We're just detecting the presence of ammonia gas. But when you do the ammonium test for your unknown, you might get some clues as to what cation your unknown might contain, depending on what type of precipitate it forms. So if, for example, your unknown contains silver ion, when you do this test, you should expect to get dark brown precipitate, silver oxide. If you have lead, you get a white precipitate. If you have manganese, you get a brown precipitate. It's hard to differentiate sometimes, but it gives you clues, additional clues as to what might be in your unknown. And these clues should be consistent to what you find doing the regular flowchart test for the cation samples.
So, Mr. Trigonometry, are we going to do the unknown substance?
You're going to do the unknown tomorrow after you finish the known. Uh-huh.
I'm a little confused on like what we're supposed to actually be recording. Like I took pictures of all like the reactions and stuff. You had said we're not using.
What I usually record is like this. Here, I record it on the flowchart, so I just write my observations on the flowchart. So 6M HCl, approximately how much did you add? This would be for the known. With the unknown, I do it on the same chart, or make a photocopy of this and do it on the second chart, or use a different color pencil. If I use the same chart, I just use a different color pen for this. For the unknown, it's going to be a bit trickier. And so what I do is, did it look like a white precipitate to you? What did it look like? They tell you it's supposed to be a white precipitate. What did this black precipitate look like? Those are the types of things you observe. If it looked okay, then you can just say check, or something like that. How much sodium hydroxide did you add?
Oh, so that's going to be it, where if we see a yellow precipitate, we could conclude that it's
Yeah,
lead to.
right.
I wasn't aware that we were just been keeping track of the exact amount.
No, not the exact amounts, approximate amounts.
Okay. I don't
Yeah, actually, you don't even need to know. As long as you know, the purpose of it, then you're fine. So for example, did you just add the amount required to, let's say, precipitate, or did you add the amount specified in the procedure? What did you do? Did you add the amount in the procedure, or did you add the amount according to your observation?
I know.
That makes a big difference.
Yeah, where I messed up in not keeping track is because when I had asked you, like if the precipitate was fine, and you said it needs to revert back to
Solution, right.
solution. So then I had to add more, and that's where,
Yeah, well, that's the type of situation here. There are a lot of details missing. So, for example, did you wash it? What happened when you cool it? When you cool it, did the lead reprecipitate out? Yes, the lead does reprecipitate out. Did you reheat it to get the lead to dissolve? Those types of things, you add your observations here. That way, when it comes to the unknown, it goes a lot faster. And so, if you just add the amount according to the procedure, then your unknown is not going to go so well. Your unknown won't go so well because of this. Let's say you have no silver and you have no lead. Do you want to add all the HCl? The purpose of the HCl is to precipitate out the silver and the lead. If you're getting no precipitate and you continue adding the HCl, then what happens is that interferes with subsequent steps. And so what you do here is, if you have no silver, no lead, you add some HCl, no precipitate. You add just a little bit more HCl just to make sure. Still no precipitate, then stop adding it, right? Because the whole purpose of the HCl was to precipitate. So if you're getting no precipitate, there's no reason to add the HCl. Is there any reason to heat it? If you're getting no precipitate, is there any reason to heat it? There's no purpose in heating it. Is there any reason to filter it? There's no purpose in filtering it. You don't know how many times the students come up to me and said, I have no precipitate, how do I filter it? Or they filter it, there's no precipitate in there, but they added all the HCl, and then they're going through the filtration and they're asking me, it's not turning black and I don't have any precipitate in there. What do I do next? Because the procedure is not going according to plan. It's not going according to plan because your unknown might not have it in there. If you're known, with your known, it's easy because it has everything. But your unknown all of a sudden becomes very difficult but it's not difficult. I mean, if you're not getting a precipitate here, just eliminate that whole branch. This is why I tell people to look at the flow chart. Don't look at the procedure, because when they're doing the procedure, they're following it step by step. And they think they're doing a good job because they're following every single step, but it's an unknown, and the unknown doesn't contain everything. And so they're actually doing a poor job because they're going down this branch and there's nothing there.
So how do you answer the post-lab question, or the observation? Can we scroll down to?
I know. You aren't going to turn in this sheet. So some people are asking me, what do I fill in? I said, don't fill anything. Just write all your observations on the flow chart.
So you're supposed to do in the flow chart?
Yeah, a copy of the flow chart. That's it. And this one, no. What you're going to do is you're going to tell me what ions you tested positive for, and I'll tell you the report format. But you're just going to tell me what ions you tested positive for in your unknown. It's like your unknown might contain silver. Well, if it contains silver, it might contain silver and no lead. It might contain both silver and lead. But whatever it is, it's not going to contain all four of these. I'll tell you that. And so what that means is the unknown can go very fast. If you can eliminate this branch here, then you don't have to heat it. You don't have to do all that stirring or whatever. If you don't get any precipitate here, you don't have to cool it. You don't have to filter. We skip these steps. And so here, if you add a drop of Ki, nothing's happening. Add another drop, nothing's happening. Add another drop, nothing's happening. Then stop adding. Move on. Don't filter. Then you're over here. When you're over here, you add some sodium bisulfate. You get a precipitate. If you get a precipitate, keep adding. If you don't get a precipitate, skip. Next. And so the unknown should go a lot faster than your known, unless you get confused with these results, which happens every semester. People get confused because what do I do next?
So where I get confused is like, when do you heat it or when do you wash it with a hot bath?
Well, that's you should have here in your observations. You heated it to get rid of the lead. Okay? That's when you heated it. Some of you will only have lead. What's going to happen is you'll get a precipitate initially, and then you heat it. All that precipitate disappears. If all the precipitate disappears, you had no silver. You only had lead. And then once it's all in solution, it's still hot. You add the Ki, and you get yellow precipitate. Some people don't heat it enough. So, for example, they don't heat it enough. This happens all the time. Somebody doesn't heat it enough, and they only have lead. They only dissolve half the lead. Half the lead remains here. They add the sodium hydroxide, it stayed white. Then they come to me and they're confused because they have no idea what just happened. It's supposed to turn black, you know. But the reason is they're supposed to heat it to dissolve, and you got to make sure you crush the crystals and get it to dissolve. But it happens every semester that somebody doesn't heat it, and they end up with lead over here, and you get confusing results. So that you got to know the purpose of the steps. You know, the purpose of the heating. The purpose of the heating is to dissolve the lead. If after heating it for a long time nothing's happening, then it's probably not lead. It's probably silver. Those types of things you put in the observations.
Are you going to want us to include, for instance, the colors of?
Yeah, you have to put in the colors. I'll tell you, the colors are going to be different. You know, it depends on what's in the unknown. The colors look a little bit different sometimes. You know, and depends on what, you know, how the separations go and other things. Overall, this works pretty well, but
So we won't have to say HCl is a clear colorless solution. Okay.
HCl, these common ones, HCl, NaOH, everybody should know HCl and NaOH. They're so common. You would write something if they didn't look normal. Like, for example, if the HCl were yellow. Sometimes it's yellow color. Yeah. It should be CCS. Or if there's a precipitate in the solution, for example, you know, in the sodium bisulfate, maybe there's some got contaminated, and there's some precipitate on there. That type of thing, you know. So be careful. Here, sometimes you don't have to do an entire branch because you don't have that, and so you could skip it.
So what is the purpose of washing it, doing the first, second, third? Well, I understand the first wash, you know, but like second, third, that's where. Like, is that just to?
No, well, it depends. You know, maybe you only need one more. It depends on how good the first wash is. The situation is we try to use a minimum amount of wash solution for the first wash. We try to use a minimum amount because we don't, if we use too much wash, this becomes too dilute. The more water that's in here, the more difficult it's going to be to detect these ions because the concentration is going down. And so the first wash, you don't want to overkill. Since that's the case, what we do is we do a subsequent wash because we want this stuff clean. So the first wash is to get, you know, some of the ions here so we don't lose them over here. The second and third wash is to get it super clean. We want this super clean because that's going to screw up this result if it's not. And so,
And does it matter if it's a hot or room temperature wash on certain ones?
this one matters.
Okay.
These are all things you need to put in your observations because these are all things that we talked about. You know. And yeah, it matters here. Like I said, here, so many people get a white precipitate here and a white precipitate here. So many people. I don't know why. You know, something screwed up. So many people get a white precipitate here. I don't know what happened. You know, people will come up to me with these bizarre results. I don't know what happened. We have to go back and figure out where they screwed up in the separation. You know, sometimes.
So when you're doing a heated wash, and you do the second and third, that's supposed to be heated as well. And if it's a room temperature wash, you stay
Well, you're fighting two things here because if there's lead residue here, it's going to precipitate out. So if your first wash is heated, that's good. If your second and third wash are not heated, it's still acceptable, you know, but it's not as good as a heated wash. It's just, if you get, you know, the second and third wash need not be heated, but if you have hot water, might as well use that. Over here, none of these washes are heated. You know, these types of things you put in the observations here. Your observations are what you did. In fact, normally in Chem 4, what I have people do is I have them, you know, do the whole thing, flow chart only, observations only, closed book. You know, that is, they can't look at the regular procedure. They have to do it based solely on their observations. And the reason for that is because that tells them if they wrote enough observations or if they didn't. You know, because if you can't repeat the experiment based on your observations, then you didn't write enough observations. And so you should be able to repeat this whole thing solely based on your observations, what you wrote down in the flow chart. And in Chem 1B, we do this, you know, but a much more involved one. In the Chem 1Bs, in some ways, it's easier. In other ways, it's more difficult. Like in Chem 1B, we don't have lead, so it's not so easy. But we have other ones in place. But it's done as an exam, you know, it's like a lab practical exam. We have these things, you know, you have them in organic chemistry too. And some of these you're going to have to do based, like the traditional one was, we had it based where we had silver, lead, and mercury. And the silver, lead, and mercury you had to analyze just from memory and your knowledge of chemical properties and chemical reactions. And so you had to devise, if you forgot the scheme, you had to devise your own scheme to do it. Normally I have this closed and then I have this individual, that is, you can't, when we do the unknown, you can't consult with your neighbor, you know, what do I do next, you know, and you can't consult with the instructor. That's a normal unknown. You have to do it entirely on your own. But since we missed last week's lab, if you have questions, I'll try to help you. Yeah. So it's not going to be as strict as I normally do. Normally it's strict, and you have to do this entirely on your own. All right. What I didn't talk about last time were the anion tests. And so in the anion mixture, which is on the lab bench, there's chloride, sulfate, and nitrate. It's a sodium chloride, sodium sulfate, sodium nitrate. So the cation's all the same sodium. We're just analyzing for chloride. Chloride, like silver ion, we precipitate silver chloride. Sulfate, no precipitate. You know, even though silver sulfate should, it depends on the concentration, but at these concentrations it won't. And silver nitrate doesn't precipitate. And so if we get a white precipitate here, with the addition of silver nitrate, then it's a positive test for chloride. We have to do this on one separate sample, that is 3 milliliters. You don't need 3 milliliters. We can get by with 1 milliliter. 1 milliliter would just be 1 spoon. This works very well. Silver nitrate solution stains everything black, so watch out. Okay, then we're gonna test for nitrate, but let's skip that. We'll test for sulfate. This one's easy. We just precipitate out with barium. Barium like sulfate, we get the ASO4. Barium chloride soluble, barium nitrate soluble. And so only barium sulfate will precipitate. This one, the nitrate test, is not metathesis. You know, this is metathesis, ion combination. This is metathesis, ion combination. The nitrate test is a redox reaction here. And so let me talk about the nitrate test and then we'll go on to break here.
So for the anion test, we skip the nitrate or?
No, we're going to do the nitrate.
But you said we skipped one. Which one are we skipping?
We're not skipping. I just skipped it for right now and changed it to sulfate. I skipped it because this is precipitation, this is precipitation. These are both metathesis. This is a redox reaction. Completely. So normally what I do for the nitrate test is just have your nitrates unknown here. And then we add up an equal amount of FeSO4 solution. And this will mix. FeSO4 is green if it's fresh. It's iron 2 sulfate. If the FeSO4 is yellow, then it's going to oxidize. It's no longer fresh. It is not good. It's got to be green. And then we mix these. Then what we're going to do is we're going to use an auto dispenser to dispense some concentrated H2SO4. The auto dispenser has a plunger. It's like a syringe. And you just pull up the plunger and then depress the handle. Actually, I drew this wrong, but it's all right. Concentrated H2SO4 is hazardous. It causes severe burns. Third-degree burn. And so what we want to do is we want to clamp this because even, it's like syrup. This stuff is super viscous. And so we use a test tube clamp to hold it. We don't want to hold it with our fingers. And then this concentrated syrup sinks to the bottom here of the test tube. So we'll build up a layer of concentrated H2SO4 on the bottom here. And then we're going to look for a reaction to occur. So this will be the concentrated H2SO4 layer. And H2SO4 is going to be a liquid layer here. And then what you're going to do is you're going to look for a brown layer here at the interface. This brown liquid layer is called the brown ring. And that would be the brown ring test. And so basically what's going to happen is this. The nitrate reacts with excess iron 2. And nitrate's an oxidizer in acid. There's some acid here. We need the acid. And when that happens, it's going to convert the nitrate to NO gas plus Fe3 plus. This is not balanced. All balanced. And then what the NO does is the NO gas combines with some iron 2 plus, this is an excess, and forms FeNO 2 plus aqueous. This is the brown layer. This is a Lewis acid-base reaction. Where NO is a Lewis base, iron 2 plus is Lewis acid and forms the adduct, the acid-base adduct. The acid-base adduct here is a very interesting ion. This is the nitrogen monoxide molecule that gets stuck on the ion here. And we have a special name for these. These are called complex ions. And anyway, it's this water soluble, and that's the brown ring. Brown ring is this FeNO 2 plus aqueous. So it's a redox reaction. This generates nitrogen monoxide. Nitrogen monoxide is hard to detect because it's colorless, but when we complex it with iron 2, it turns the color brown. Okay, then we're going to discard this into the waste, because you got to watch out for the concentrated H2SO4. It's a quick test. It only takes a few minutes. Let's do all, these are all very quick tests.
So gloves are recommended.
Yeah, gloves are recommended. Even, you got to watch out. If you have latex gloves, H2SO4 will eat up the latex gloves. So even with gloves, you should exercise caution. All right, are there any questions on this? Okay. All right, let's take a break and then start again. So the quiz for the this is what I've been looking for. The 1s to the 2s is going to be the biggest jump here, and then the 2s to p, small jump. This would be the second shell, third shell here, 3s 3p, and then the gaps start to become smaller. So here I need to see the 4s is lower in energy than 3d. There should be 5 orbitals for the 3d, and then the 4p. Up here. So this goes to the fourth shell. There are also some questions here. I don't know if you had a chance to look at the quantum number problems. Did we look at these?
I don't think we did that.
Well, the answers are in the back there, but let's just see if you guys can answer them now. What can you say about the spin quantum numbers of 2 electrons in the same orbital? They have to be opposite. One has to be plus, the other has to be negative. Because there's a principle. Do you know what the principle is that says no 2 electrons in an atom can have the same set of 4 quantum numbers? The first 3 quantum numbers, NLM, tells us what orbital. The 4th quantum number tells us spin up or spin down. What's that principle? Hunses, they have to fill, when they're energetically degenerate orbitals, they have to fill singly with Carlos. It's Pauli, the Pauli exclusion principle. And so the Pauli exclusion principle tells us that no 2 electrons in an atom can have the same set of 4 quantum numbers. In what subshell is an electron located if its quantum numbers are? Okay, so the subshell would be an S subshell, the P subshell, the D subshell, the F subshell. Which of the quantum numbers tells us the subshell? Well, N tells us the shell or the, it's a little bit tricky because there's some overlap, but N is the energy. L is the subshell. L equals 0 is the S. L equals 2 is the D. And so this is the S subshell, this is the D subshell. You can tell by the L. 3, what are the values of N and L for an electron in 3p? orbital. Well, yeah, 3, and a p is what? L. 1, yeah. So this would be 3, 1. 4f would be 4, and f is 3. All right? Yeah, f is 3. What are the possible values of L in the 4th shell? In the 4th shell, what do we have? We have the 4s, so that's L0. 3d, L2, and the 4p, is L1. The 3d subshell, well, there's only one possible value of L, and when it's a D, L is 2. What are the possible values of M in a P sublevel, P subshell? Subshell and sublevel are the same thing. So what are the possible M values? -1, 0, 1. Yeah, -1, 0, 1. They're based on L, L0, 1. The F subshell.
-3 to +3.
Yeah, -3 to +3. Yeah. 7 values altogether, 1 through 0. 6. You know where all these come from? These all come from the Schrodinger equation. You know, the mathematical prescriptions to answer the Schrodinger equation. So these all come from that. There, you know, for the hydrogen atom, there are an infinite number of solutions of the Schrodinger equation. You aren't going to list an infinite number of solutions out. Rather, you're going to come up with some mathematical patterns so you can figure out what the solutions are. Otherwise, it's too many to write out. And so this is why we do this kind of stuff here. 6, in the ground state of krypton, how many electrons have m sub L equal -1 as one of their quantum numbers? How many with L equals 2? And this one, skip this one. I don't like that particular question.
We don't have to turn this in, do we?
No. All right, construct an energy level diagram for each ground state. Ground state just means you fill the lowest to the highest. Okay, construct an atomic orbital diagram. So what's the difference between an energy level diagram and an atomic orbital diagram? What's the difference between those? Well, in an energy level diagram, we have the energies on the y-axis. In an atomic orbital diagram, these are atomic orbital diagrams here. Energies just go left to right here. We don't try to show the scale. I mean, all the gaps are the same. So the gap between the 1s and 2s are the same here, and the 2s and 2b are the same here. So this doesn't really show the relative energies, the magnitude of relative energies. So energy level diagram is more descriptive, but it takes up a lot more space. What's much more compact is the atomic orbital diagram shown here. What's even more compact than that is this. What's this called? You spell it out. CNF would call it what? Electron configuration. Electron configuration is the most compact, especially using noble gas cores. But you're missing information. The type of information you miss are, are the electrons all paired? Here's one unpaired electron. Here's two unpaired electrons. There's two unpaired electrons. The rest are all paired. Here, all the electrons are paired. And you're missing the relative energies. And so this is the most informative, the energy level diagram. The next most informative would be the atomic orbital diagram, or the orbital flux diagram. And the least informative would be the electron configuration here. But it takes up the least amount of space. That's it. Can you identify this element? Neon. Yeah, first and second shell fill. How about this one?
Copper.
Nickel. Not copper. Close. It's close to copper. Not iron. nickel. This is nickel. 4s2, it's argon, 4s2, 3d8. And so when we look at the periodic table, you know, argon fills the third shell, 4s1, 4s2, 3d1, 2, 3, 4, 5, 6, 7, 8, 3d8 would be nickel. That's what we have here. And so when we look at the 3D, we have 2, 4, 6, 8 electrons. How about B? What element is that? Fluorine. E? Silicon. C? What is it? So, selenium, okay, yeah. 4s2, 3d10, 4p1, 2, 3, 4, selenium. 4p4. This one, I mean, this is this is a special exception. 4s1, 3d5 is chromium. And then, take a look at some of these other practice questions on the periodic table. The third period element with 6 electrons in its outermost principal energy level. That's kind of third period element, third shell with 6 electrons, 6 valence electrons. So from the third shell, what element has 6 valence electrons? From the third shell, so sodium, magnesium, what has 6 valence electrons? Sulfur. Sulfur has 6 valence electrons. So that should be sulfur. The third paired element with 3 unpaired electrons. 3 unpaired electrons.
Phosphorus.
It's got to be phosphorus. A fourth period element with a half-filled D sublevel. Fourth period element with a half-filled D sublevel. There are 2 of them. So fourth shell, half-filled, excuse me, would be what? Chromium and manganese. This would be both half-filled. So they're only asking for 1 at this time. 4, a transition element containing a completely filled 4D subshell. Transition element 4D. So the first D is 3D, and then we have the 4D. So what transition element has a completely filled 4D? Cadmium. Before, this would be 4, this would be 5s2, 4d10. The other one would be silver, because silver is 1 electron short of filling it, and so it promotes one of the 5s electrons to fill that. So silver would be similar to copper. So, etc. We're going to skip the rest of these, except for these 12. The period 4 element with the highest first ionization energy. So if we're in the fourth shell, what one should be hardest to ionize? Out of all these elements here, which one should be the hardest to ionize? Well, what happens with size? Is it biggest on the left or the right? Which atom is bigger? So, for example, potassium versus krypton. Which one's bigger? Potassium is bigger. And the atoms get smaller and smaller. And so as it gets smaller and smaller, the smallest ones will be the hardest ionized. So therefore, krypton's the smallest, which should be the hardest ionized. The other way to know this is krypton's a noble gas. Noble gases are extremely difficult to ionize, all of them, because they're still shell. So the period 4 element with the highest first ionization energy is going to be krypton. The group 2 element with the lowest ionization. Lowest should be easiest to ionize. Easiest to ionize should be the biggest. And so if we're in group 2, which is the second column here, which one of these is the biggest? Radon. So radon's going to have the lowest. But radon's radioactive, so we might say barium. Okay, X is the element with the lowest ionization energy. Lowest ionization energy should be the biggest. The biggest is going to be in the bottom left, X here. Y is the most reactive nonmetal in this table. 17, which would be fluorine here. Fluorine really wants an electron. That would be Y there. Q has only one proton in its nucleus. That's got to be hydrogen. So Q goes here. I wonder if this spells out the word or something. R and T have 8 electrons in their outermost principal energy levels. T atom is larger than R. So if 8 electrons, that means it has an octet. So it has an octet. Helium would have a duet, and then neon and argon would have an octet. So which one's bigger? Argon's bigger. So T goes here. Atoms of elements A and E contain 3 unpaired electrons. E is more metallic than A. 3 unpaired electrons would have to be half-filled P. And so it'd be here and here. A half-filled P would be nitrogen and phosphorus. Yeah. Which one is more metallic, though? Neither. They're both non-metals. But which one's more metallic? Well, the one that's the most metallic element is going to be on the bottom left. It's cesium or francium is the most metallic. And it's going to have properties like that you expect from metals. And as we go further and right and up, it becomes less metallic. Periodic table. So if we're going to pick one as being more metallic, we could pick phosphorus. And so E would be here. A would be nitrogen. Atoms of Z E would be here with phosphorus. It would be more metallic because it's lower down than nitrogen. The most metallic would be down at the bottom left. The least metallic would be at the top right. Atoms of Z contain 7 electrons in the highest energy shell. So 7 electrons in the highest energy cell would be fluorine and chlorine. But I think we would pick one of those. Fluorine, so it would be chlorine. Ki forms 2 plus ions with electron configurations identical to atom R. HR forms, well, 2 plus, where's 2 plus? It'll be in group 2. 2 minus will be in group 16 here. Element J has 1. Dr is a noble gas. Kx is metalloid. So you can go through and do those. Some of the questions there. This is the key here. So there's no secret text message, I think. It would have been more interesting. Anyway, some orbital box diagrams or orbital diagrams, some energy level diagrams here.
For the orbitals,
Mhm.
would you, I didn't check the test, but would you ask us the shape?
Yes. SPD. S is what shape? Spherical. P is like a dumbbell shape or figure eight or something. And the D is, yeah, 4-leaf clover. That's it. F, I'm not going to ask you F. Have you seen the shapes of the higher orbitals? Did I show those to you? Yeah.
Mm-hmm.
They're quite complicated. All right. Just some review for the I'll just continue with the PowerPoint. We left off in chapter 18, right? Talking about collision theory, did we?
I thought we were in chapter 17.
Chapter 17. Did we do pH in chapter 17? We
We
didn't?
talked a little bit about it. You ended at the equilibrium.
Okay. This is where I left off. The water equilibrium.
Yeah, it was pretty much there, yeah.
So wait, did you jump?
Before that,
Right there.
right there. Maybe someone out of sync.
When I crashed your other class, I remember on Wednesday, you were on the chart, strongest acid to the weakest, and you were explaining about how hydroxide could be looked at as like a very, very weak acid. So,
Yeah. Yeah. I was talking about what conjugates there.
conjugates, there we go.
All right. If I have a glass of pure water at 25 degrees C, it's mostly water molecules, but there's this curve. Let's look at this. What's this called? Maxwell-Boltzmann distribution, and it shows us the population versus the kinetic energy. And there's going to be a high energy cutoff here. If we have energies above this, that's enough energy to break bonds here. And so if this hydrogen here is attacked by this oxygen here, we show that using an arrow here like this. So what happens is this lone pair here gets pushed into the hydrogen and it creates a new bond, and this bonding pair gets pushed out. And so we end up with something that looks like this. This reaction is not favorable because this is the base here, which is a proton acceptor. This is the acid here, which is losing the proton or the hydrogen. And if we go backwards here, this is going to be the acid here. This is going to be the base. So when we compare the two acids, hydronium versus water, this one's much weaker, this one's much stronger. And as far as the bases go, water is a much weaker base than hydroxide. Hydroxide is a very strong base. And so the driving force is to the left. And so this is what we call a very energetically unfavorable reaction. That is, if we have two waters here, it's much lower in energy than converting that to hydronium and hydroxide. But I mentioned that, let's say you had a 1 billion population of water molecules at 25 degrees C. Not all water molecules are going to have the same energy. You're going to have a distribution. Most of these water molecules don't have enough energy to climb this hill. It's deep. This is a tiny, tiny fraction of these water molecules will have enough energy. Do you remember or recall how many? If I had a billion, about how many water molecules can make it up to the top of this? About 4. 4 out of a billion. If it's only 4 out of a billion, most of the time we'll just ignore it. You know, it's so little, it's negligible, isn't it? Just 4 out of a billion. But, you know, even though it's so small and negligible, it's actually something we can measure. And so in pure water at 25 degrees C, we end up with 1.0 times 10 to the minus 7 molar, which would be 0.1 micromolar hydronium, and 1.0 times 10 to the minus 7 molar hydroxide, which is also 0.1 micromolar. And so a tiny fraction does react, and this tiny fraction we can measure using a pH meter. If we measure using a pH meter, the pH measures the power of the hydrogen ion concentration, the negative power of the hydrogen ion concentration, which is 7 here. And so this is going to give us pH 7.00. We could also measure the power of the hydroxide ion concentration, but usually we just measure these because these are tied together. And so there's a seesaw relationship between the powers. And that is, if one goes up, the other has to go down. In this case, both are equal. So water has a pH of 7. We can measure that. And water is neutral, though. Neutral just means that we have equal amounts of acid and base. Here. What happens if the temperature changes? If the temperature changes, that is, if it gets hotter, the pH changes. You know that? If this gets hotter, what happens to the Maxwell-Boltzmann distribution? It shifts to the right. And if it shifts to the right, the population of higher energy molecules is going to go up, which means the concentration of this goes up. The concentration of this goes up. Do you know what happens to the pH? So let's say rather than being 10 to the minus 7, it's 10 to the minus 6. If it's 10 to the minus 6, what's the power? The power would be 6. So as the temperature increases, the pH actually goes down. As the pH goes down, it becomes more acidic. However, it's still neutral because we have the same amount of hydronium and hydroxide. So this is a headache. This pH depends on temperature. And so what we do is this. we have a normalized pH, and the normalized pH is this. The pH of pure water is always 7, regardless of what the temperature is. And so we make sure that the pH of water always reads 7. How we do that is with electronics. So if you have a pH meter, yeah, the pH is going to be changing, but the electronics is going to correct it. And so it doesn't matter what the temperature of the water is. Pure water is always going to be pH 7 because what we do is we just reference that back to room temperature, 25 degrees C or G. And so in the old days, you had to do this by hand. When you had a pH meter, what you do is you put it in pure water and then you adjust the temperature knob so that the pH reading is correct, pH 7. Otherwise, the pH is always changing the temperature, which is really a hassle and annoying. Modern day pH meters, you don't have to do this. Modern day pH meters, they have built-in temperature adjustment there so that no matter what the temperature is, the water is always reading pH 7. This makes your life easier. What pH 7 means is that, okay, you have equal amounts of hydronium hydroxide. Because the pH plus the pOH has to equal something called the pKW. pKW is 14.00. So these two have to add up. So if one goes up, the other has to go down by the same amount. And then we get that. And so here, the pKW comes from something called KW. And so there's some mathematical relationships which we look at here. We talk about, this is the reaction here. This reaction is very uphill. The mathematical relationships are shown in this table here. You don't have to memorize any of these. So basically, if we're given one of these, we can figure out all the others just because of how they're all interrelated. So if we know what the pH is, then we can figure out the H plus concentration. So if we know the pH, we can figure out the H plus. Once we get the H plus, we can figure out the OH minus concentration because they're tied. If one goes up, the other has to go down. Or if we know what the pH is, we can figure out what the pOH is because the pH and the pOH have to add up to 14. And if we know the pOH, then we can work backwards to get the OH minus. And so this is just using the properties of logs. We aren't actually going to do any of these calculations. But we do these in Chem 4. Okay, once we do that, then we see these relationships. If we have pH 7, then the pOH is 7 because it has to add up to 14. So if the pH and pOH are the same, then the power of the hydrogen ion and the power of the hydroxide ion concentration are the same, which means that they're equal, and the solution will be neutral. If we have more acid, then its pH drops below 7. This has that inverse relationship because of the negative there. Then the pOH is going to be greater than 7. So if the pH goes to 6, the pOH has to go to 8. Compensate. And so that means we're going to have more. 10 to the minus 7 is more than 10 to the minus 8. If the solution is basic, then pH is greater than 7. So what you should know is this. Here. pH is less than 7 are acidic. pH is greater than 7 are basic. And they could be strongly acidic, strongly basic. And the pH scales are usually shown from 0 to 14. But can we have pHs less than 0, negative pHs?
Yes.
Yeah. In fact, have you heard of Iron Mountain, California? Did I talk about that? I talked about Canada. The lake in Canada? Mm-hmm. That was another class. Yeah, I guess I didn't. I thought it was ahead in this class, but we got it opposite.
You were behind in the other class, ahead in this one. And then it flipped.
It flipped. Well, Iron Mountain is in Redding, California, and it's a Superfund site. And why is it a Superfund site? Iron Mountain mine disaster. You know what the pH of water in Iron Mountain is? Not negative 14. That's a little bit too extreme. Inside a toxic hellhole, Iron Mountain mine. Iron Mountain has the lowest recorded pH of any natural water. So let's see what that pH is. Maybe 3.6. Now I should say natural water. I don't know what this is either. Yeah, this negative negative pH and extremely acidic mine waters from Iron Mountain, California. What's that?
What happens if you drink?
You wouldn't want to drink this. Stomach acid is like pH 0. This is negative 3.6. That's like 1,000 times, almost 10,000 times more acidic. Can you imagine that? Because it goes by orders of magnitude, powers of 10. Extremely acidic mine waters with pH values as low as negative 3.6. Iron Mountain, California, the Richmond mine. These are the most acidic waters known. The pH measurements were obtained by using a Pittsburgh method. It's hard to measure these extreme pHs. Because pHs go non-linear. You know all the equations I just showed you? They don't work once. A lot of people, they don't work when interested in research.
So everything we're being taught is a lie.
No, it's not a lie.
It's like, I know.
This isn't open water though, right? It's like underground.
It's underground.
Oh. They won't listen.
The equations that I showed you work okay from 0 to 14. If you go below 0, you need to use fancier equations.
What makes a pH negative?
This is the concentration. What's that? Yeah, just from waters going through the tailings. The tailings are the waste products from the mines, just rocks and whatever else that they don't use. You know, there's another one. I was driving out by Mojave. There's a silver mine out there. And yeah, they use a lot of cyanide. And so they had to cover it. Otherwise, cyanide was just going across the freeway, cyanide salt. All right, a pH of 0 means that the H plus concentration has 10 to the minus 0 molar concentration. 10 to the minus 0 is what? Is 1 molar. If I have the H plus concentration of 0.1 molar, what would the pH be? Well, 0.1 molar would be 10 to the minus 1 molar, and therefore the pH would be 1. And so if we go 0.1 molar, 0.1 molar has a pH of 1. 1 molar has a pH of 0. Is 1 molar very concentrated? 1 molar HCl? Would you call that concentrated or dilute? 1 molar HCl is going to give us 1 molar H plus concentration. The 1 molar H plus concentration gives us a pH of 0. This is what we call dilute acid. 1 molar. What's concentrated? Concentrated is like 12 molar HCl. Even if we have 6 molar HCl, 6 molar is still considered dilute. 6 molar HCl is going to be this. If we calculate the pH is equal to the negative log, this is the equation that we use, times the H plus concentration. And so it's the negative log of 6. What is the negative log of 6 equal to? Negative 0.778. And so the pH of 6 molar is already negative. It's negative 0.7, negative 0.8.
Oh my god.
If we go to 12 molar HCl, 12 molar HCl is considered concentrated HCl. This is as concentrated as you can get. Or no, we can go to 18 molar. Let's go to, well, we'll just leave it at 12 molar. 12 molar HCl is concentrated. That should give us 12 molar H plus. And so the pH is equal to the negative log of the H plus concentration. Because all power functions are equal to the negative log. And so 12, this gives us a pH of negative 1.07. So that's the pH of that is negative 3.6. Now there's problems because once you get to very high concentrations, the equations don't work so well. And so these equations have to be modified. And so with pHs below 0 and above 14, you could have pHs above 14. Need special equations. These special equations, this is a branch of chemistry, it's physical chemistry. That we do that. And so in Chem 1A and Chem 1B, we don't do this. These special equations. Talk a little bit about it. And therefore, a lot of people think that the pHs can't go below 0 and above 14 because they always see 0 to 14. But the pHs can extend beyond those ranges. So it's just between 0 and 14 you can use the regular equations. Above 14 and below 0, we have to use the special equations. Yeah. And that is when the concentrations get high, the behavior becomes nonlinear. So here we can see just the power and the pH. So what types of questions?
What does nuclear waste due to the water, does it make it more acidic or?
Nuclear waste?
Yeah,
What kind of nuclear waste?
not just like,
Radioactive?
Yeah, when there was a disaster in Japan and it contaminated the water.
Yeah, that kind of waste, like metal waste, usually makes it more acidic. I don't know what the pH is, but that would be interesting to see. The pH is this. We aren't really getting into it too deep, and so this is probably even beyond. If this is 0.01 molar sodium hydroxide, then it's going to be 0.01 molar hydroxide. 0.01 molar is 10 to the minus 2. So the pOH would be 2. If the pOH is 2, then the pH is 12. And if the pH is 12, then that means the H plus concentration is 10 to the minus 12 molar. So those are the types of calculations we do, just with integer values here. We could do the math pretty easily, but for values where we have a coefficient, we have to plug that in. So this is 2.7 times 10 to the minus 6. It's not 1 times 10 to the minus 6. If this were 1 times 10 to the minus 6, it'd be easy. The power is 6. That would be the hydrogen. So the pH would be 6. The pOH would be 8. Hydroxide would be 10 to the minus 8 molar. But now we have this coefficient, which is not 1. And so here we have to plug it into the equations. And these equations, we're not going to do any calculations. This is optional. I'm just going to skip this. There's a funny thing that happens with power functions. The coefficient has 2 sig figs. In a power function, everything after the decimal is significant. And so this only has 2 sig figs too. It's a power function. Power functions, the sig figs are after the decimal. But you can go through the rest. And so we skip this. We skip the calculation. And so the basic thing for pH is this. We have this happening in pure water. Now, if we add acid to the water, that's going to increase the hydronium. If it increases the hydronium, it's got to decrease the hydroxide because the hydronium and the hydroxide have to maintain a certain constant. That is, if one goes up, the other has to go down. And the constant is this. It's called Kw. Kw is the water constant. And it's 1.0 times 10 to the negative 14. And this has got to equal the hydrogen ion concentration times the hydroxide ion concentration. So if both of these are 10 to the minus 7 molar, that's going to give us 14. We can also do this in terms of power functions. The pKw is going to equal the power of the Kw. The power of the Kw is 14 to 2 sig figs. 14 to 2 sig figs in a power function is going to be 2 decimal places like this. And so these are the same here. And using the property of logs, it's going to equal the pH plus the pOH. Because the power function is negative log of those. So we could use that. So this would be the same kind of thing. So again, we're not going to do any calculations with this. We're just going to do a brief kind of overview.
Don't worry about calculations.
Don't worry about calculations. I didn't give any calculations for this. What you do need to know is acid has pHs less than 7, bases have pHs greater than 7. That's about it. Let me see what the questions I have.
So obviously there's calculations in the homework, right?
In the homework, there are calculations. In the homework, the calculations is just for just for what should I say, experience. So we can take a look at all the types of questions we have for pH.
I'm confused. I know this doesn't require calculations on the test. There was another chapter that you said don't worry about the calculations. Was that the gas stoichiometry or?
No, gas stoichiometry, you have to worry about the calculation. The gas stoichiometry. What else?
There was one calculation.
Well, there are a number, like, for example, normality.
Normality.
Titrations of normality. You don't have to worry about calculations. In chapter 18, there are a bunch of calculations you don't have to worry about. Those are equilibrium calculations. I'll talk about them, which are this. This is what we call dynamic equilibrium. All these pH calculations, we use similar calculations for other reactions that are in chapter 18, which we'll talk about. But first, we'll just take a look. Of what significance is a very small value of 10 to the minus 14 for Kw, the ionization equilibrium constant for water? The very small value is there's very little hydrogen ion and hydroxide ion formed in the reaction. And so, this is very small. Because we get very small amounts of hydrogen hydroxide because it's a very unfavorable reaction. And so most of the water molecules are going to stay down here. Very few water molecules will make it all the way up top here. And we'll reach some sort of dynamic equilibrium here, where the rate of molecules going up is equal to the rate of molecules going down. But most of them are going to be here. And so 1 billion of the water molecules will be here, about 4 of them will make it up to the top. How is it that we can classify water as a non-conductor of electricity and yet talk about the ionization of water? If it ionizes, why does it not conduct? So pure water at 25 degrees C is different than tap water at 25 degrees C. Tap water at 25 degrees C conducts electricity pretty well. The pure water at 25 degrees C is an insulator. It's an insulator because we don't have enough charge carriers. There are some charge carriers here, but 4 out of a billion isn't enough to conduct much of the current. And so pure water has what's called mega ohm resistance. In fact, that's how we test the purity of water. When I was working with high purity water, there was a ohm meter attached to the water, and you would just read the ohm meter to see how pure the water was. And if it was registering the mega ohm, then it was good, clean water. But even the good, clean water is still going to be 10 to the minus 7 molar, hydrogen 10 to the minus 7 molar hydroxide. And so you might think that this is a weak electrolyte. Weak electrolytes are partially ionized, but weak electrolytes we expect a little bit more, maybe like 99.9% and 21%. But this is such a small percentage that you call a non-electrolyte. Technically, it's not. But we call it non-electrolyte because the hydronium hydroxide is so small. And so if it ionizes, why does it not conduct? It doesn't conduct because there aren't enough carriers in solution. 39, if the H plus is 10 to the minus 5 molar and the OH minus is 10 to the minus 9. So 10 to the minus 5 times 10 to the minus 9 is equal to 10 to the minus 14. It has to equal 10 to the minus 14, that would be Kw. Is the solution acidic, basic, or neutral? So is that acidic, basic, or neutral? Well, which one's higher, the H plus or the hydroxide? Which one has a higher concentration? Well, it's a little bit tricky because this is 10 to the minus 9 and this is 10 to the minus 5. And since it's the negative, it's actually 10 to the minus 5, 0.0001 versus point, you know. And so this is going to be 4 zeros and a 1 molar. And the OH minus is going to be 8 zeros and a 1 molar. And so 10 to the minus 5 is greater than 10 to the minus 9, which means it's acidic. How do you know? Whichever one's bigger. That's going to tell you that it's acidic, basically. An aqueous solution has a hydrogen ion concentration of 10 to the minus 4 molar. What is the hydroxide ion? Well, this one we are not going to do necessarily. But what would the power of the hydrogen ion concentration be? The pH be? If it's 10 to the minus 4, the pH is 4. If the pH is 4, is it acidic, basic, or neutral? Acidic. That's how we had that question. This is a calculation here. An aqueous solution has a hydroxide ion. You might have a calculation here. You'll have to use the equation to do it, but you're going to have to do it on this test. And then we have some integer values here. We'll take a look at some more of chapter 17. But what I need to do is we need to get started with chapter 18. Chapter 18 deals with chemical equilibrium. And so this is a chemical equilibrium here. This is dynamic equilibrium. It's a chemical equilibrium because this reaction can go in two ways. It can go forward or it could go reverse. And what we have, because of the Maxwell-Boltzmann thermal distribution, we have a constant population of water molecules that have enough energy to react here. And so even though hydronium and hydroxide love it to react, you know, hydronium reacts with hydroxide to form waters. And so if a hydronium comes in contact with hydroxide, we're going to have an acid-base reaction that's going to fall back down. But as soon as that falls back down, it's replaced by another collision here that brings that. And so this dynamic equilibrium just means this is going in circles, but there's no net change. Since there's no net change, this concentration of this is stable. The concentration of this is stable at 10 to the minus 7 molar, pH 7. And the concentration of this is stable at 10 to the minus 7 molar. That would give us a pOH of 7. And so the pH is stable, but this is a chemical equilibrium, dynamic equilibrium. Now, for chemical equilibriums, we use K to tell us. Chemical equilibrium, we have this is called the equilibrium constant. And the equilibrium constant is going to be proportional to the product's concentration over the reactant's concentration. So the bigger the K, the more product at equilibrium. The smaller the K, the more reactant at equilibrium. And so here we see a very small K, which means it's mostly reactant, very little product. We can do lots of calculations with K. That's what's involved in these pH. And the same thing, not just this reaction, but we could do it for many reactions. And so, for example, this reaction, there's a forward and a reverse. And so we could just look at the balance. Is it product favored or reactant favored? If it's product favored, then K is big. If it's reactant favored, K is small. And then we can do calculations. Well, we aren't going to actually do any calculations here. We're just going to be looking at this. And so usually we show these equilibriums by using a double-headed arrow. And so for this equilibrium, we show it like this. H2O liquid plus H2O liquid is going to be in equilibrium with HCl plus and OH minus. Now, the double-headed arrow doesn't show which way is favored. In this particular case, the reverse reaction's way is favored. And so sometimes what people do is they'll draw a small arrow up, meaning very little makes it up, and then a big arrow down, which means it's biased downwards. And so this is one way of showing that this equilibrium is favored to the left, we say, to the reactants. The other way of showing this is by the K. K is 10 to the minus 14, which shows that the ratio of product to reactant is very heavily biased towards reactant. And so this is two ways to show the bias. One is write the K value. Two is to draw uneven arrows like this. So that shows us. And so the uneven arrows would be like this. All right, the closed system we don't have to worry about. Closed system, we treat everything like a closed system. But we have this dynamic equilibrium. This we have to worry about because this is a dynamic equilibrium. Dynamic equilibrium is just going in circles. Dynamic equilibrium means the forward rate is equal to the reverse rate. It's not really shown here. You know, when we have equal size arrows, it's shown. Well, equal size arrows don't show the bias. This is heavily biased towards reactant than product. You know, reactants are much more stable energetically than product. And so dynamic equilibrium is a state in which the opposing changes occur at equal rates. That's a dynamic equilibrium. It results in zero net change over a period of time. This results in zero net change. The pH should be stable, pH 7. The forward and reverse rate of change are equal in equilibrium. Well, that's what's happening. For every water that forms, one water goes back out and reverses that. So, all right, now we could do the same thing here, but we aren't going to do it with the numbers. In fact, you don't even have to pay much attention to this slide or this graphic, because this is a weird choice for showing dynamic equilibrium. And I mean, there are much easier ones to do than this. This one's just complicated. All right, what's happening in this? We're going to take a look at this in a little more detail. And we're going to look at the collisions. Now, not only do these collisions have to have enough energy, there's one other thing that these collisions have to have, and that's the correct orientation. And so even though they might have enough energy to react, if the orientation isn't correct, then we're not going to expect any reaction. So out of this big population here, there's actually more than 4 that have enough energy to react. But the problem is they aren't oriented correctly. So if we look at the 2 water molecules here, we need the oxygen to attack the hydrogen on the other. But if we have the 2 oxygens collide and they have enough energy, we aren't going to get any reaction. And so here the oxygen tries to attack the oxygen, nothing's going to happen here. And so there's no reaction here. Or likewise, if the hydrogen collides with the hydrogen, in this case, if the two hydrogens collide, there's no reaction here. What we have to have for a reaction to occur is we have to have the oxygen collide with the hydrogen. And so that's what we mean by having the correct orientation. So all these three might have enough energy, but if we don't have the correct orientation, not all three react. Just the first one will react in this case. And so when we're looking at a collision to be successful, it has to have the correct orientation and enough kinetic energy to break the bond. And so when we're looking at the Maxwell-Boltzmann, that's only part of it. The Maxwell-Boltzmann tells us the population that has enough energy. But out of that population, there's an even smaller population that has the correct orientation, which I ignored when I looked at it originally. And so in this slide, there are two things needed for a collision. We can see that here in this. There's a molecule here colliding with the molecule here. This is the correct orientation and the correct energy. If it didn't have enough energy, they just bounce off one another. But this one has both. And so what happens is we break bonds and we form new bonds and we get product. Here, this might have enough energy, but the orientation's bad. And so they just bounce off. And the same thing here, orientation's bad, so they bounce off. And then, of course, we could have the correct orientation, not enough energy, or the incorrect orientation, not enough energy, and get no reaction. And so, again, we need two things for a reaction: correct orientation and enough energy. Okay, when we do this, we can map it out here. So we're going to have A2 and B2 react. So here's A2 and B2. One, it has to have enough energy. How much energy? Well, the amount of energy is what we call EA, the activation energy. And so it has to have enough energy here to climb this hill to break the bonds. If it doesn't have enough energy in the collision, it just falls back. It bounces off and falls back. So we need enough energy to climb over this. And then we need the correct orientation. This is called reaction profile diagram. The reaction profile maps out the collision here. So we have a collision between A2 and B2. They collide. They have to have enough energy. If they have enough energy, then they can drop down to product. This is it. Delta E is the energy change overall. And so the energy of the reactants is here, energy of the products is here. So delta E, this is exothermic. We're going downhill. But even though this is a favorable reaction, the products are more stable than the reactants. It has to overcome this barrier first. And so there are lots of examples of this barrier called the activation energy. One example is this, methane. We know methane and oxygen react favorably, but at room temperature, it's very slow. So if I leak out a whole bunch of methane here, nothing happens. And nothing happens is because it has to overcome this hump. If I have a spark or hot surface, then I can get enough to overcome this hump, and then we get reaction. So let's see, activation. So when we're looking at the collision, here we have this collision. This one we'll just ignore that. Transition state. This one we'll look at here. At the top of this peak here is what we call a transition state. The transition state is the state where the bonds are being broken and the bonds are being formed. And so we need to break the AA bond, the BB bond, and form the AB bonds here. The transition state's never isolated, it's at the top of this. Instead, what we end up with are products here, the two ABs. And so this would be a successful collision here. This is just showing here enough kinetic energy to overcome the activation energy, not enough energy to overcome the activation energy here. If we change the temperature, then that's going to change the population. So here's the activation energy, the minimum amount of energy required to react. And so at room temperature, the population is smaller. At 75 degrees C, the population is greater. And so we're going to get more reaction here at higher temperatures. So the rate of reaction, that is the speed of the reaction, increases with higher temperature because we're going to have more molecules with enough energy to react. All right, there are certain things. Temperature will influence how fast things react. But we also have catalysts. Catalysts, what they do is they provide an alternate path for reaction. And so what a catalyst is going to do is it's going to lower the activation energy. And so when we put a catalyst in here, it provides an alternate pathway. The alternate pathway has a much easier or smaller hill to climb. And therefore, it's going to speed up the reaction. So in catalysts, there's substance that increases the rate of chemical reaction by lowering the activation energy. They lower the activation energy by providing an alternate path to reaction. Molecules with lower kinetic energy are able to pass over the potential energy barrier. That is, the population increases because you don't have to have as high of energy to react. Inhibitors, substance added to a chemical reaction to retard its rate. And so inhibitors are usually for catalysts. And so I'm not going to get into it. Inhibitors inhibit catalysts. And so here we see how the catalyst lowers the whole. It lowers it by providing an alternate path. And so if we take the normal reaction has this huge activation barrier. A huge activation barrier means it's going to be slow because the population of molecules is going to be small. Whereas if we put a catalyst in, the population is going to grow significantly because the activation area is much lower. And so it's a much smaller barrier, so more molecules can climb the hill. And so the double hump here just shows that there's a different path here, consisting of different collisions. Each of these humps is a collision. And so in that case, it's been replaced by two humps, two collisions there. Here we can just see in terms of the Maxwell-Boltzmann distribution, without catalyst here, with catalyst here. So the population is going to be much bigger and we'll get a faster reaction. Other things that can impact the rate of the reaction would be concentration. The higher the concentration, the more collisions. The more collisions, the faster the rate. And so high concentrations, fast rate, low concentration, slow rate. It's just in terms of collisions. All right. This is a weird chapter because this collision theory is primarily concerned with how fast the reactions occur. It's kinetic. But when we're talking about equilibrium, this is the hill. How high is the hill that we have to climb? Or maybe it's downhill. You know. And so when we're looking at equilibrium, we care about, how many of that population can make it to the top of the hill. And so this. Let's skip this one. All right, so once we establish this, there are two things we would look at. This is the equilibrium part of it here. The kinetics part of this is looking at something called the reaction profile. And so the kinetics part of this is we're down here at H2O liquid plus H2O liquid. And what we'll have to do is we'll have to have a collision occur. And the collision is going to have the right orientation and the right energy to climb up the hill. That's going to be EA here. And then once we do that successful collision, then it'll drop down the product. In this case, the product will be up here. This will be hydronium and hydroxide. And so in kinetics, we look at this part. In the equilibrium, we just look at this part here. Excuse me. And so what do they say here? Development of a chemical equilibrium. And so when we're looking at equilibrium, we're just looking at this, the forward and the reverse. We want to get from reactants to products. In kinetics, we have to go through this thing with the activation energy and the transition state. The transition state we don't actually isolate. That's going to be at the top. The transition state is going to be some kind of state where the bonds are breaking and the bonds are forming. Like that. There's going to be some kind of weird transition state here. And then these are the products. So, but I don't really like this slide. This is just showing the reaching of equilibrium. And so initially, let's say we have nobody at the top here. If we have nobody at the top here, there's going to be a collision here, which is going to result in people climbing to the top. And so that's the forward reaction here. The forward reaction here. And then once people make it to the top, they'll fall back down. That's this one here. And so initially the rate of the reverse reaction starts at 0. The rate of the forward reaction is at max. Then what's going to happen is as the population grows up here, that means more molecules are going to fall back down here. And so as the population grows, the rate increases for the reverse. And ultimately, the rate decreases for this. Eventually, the rates will match the overall rate here. And here we hit the state of dynamic equilibrium. When we hit the state of dynamic equilibrium, let's say 4 water molecules react to go up, and then 2 of these react to go down. And so we hit the state of equilibrium. That's what this is trying to show. But you don't need to worry about that too much. Once we establish equilibrium, then we have something called Le Chatelier's principle. Le Chatelier's principle says if an equilibrium system is subjected to a change, it's going to counter the change to reestablish a new equilibrium. And so what this is showing is if we perturb this equilibrium here, a new equilibrium will be established. So one way of perturbing this particular equilibrium is if we add acid. If we add acid, what's going to happen is it's going to react with more hydroxide, it's going to drop down. And when that happens, it's going to reestablish a new equilibrium. So if we increase the hydronium, the hydroxide goes down. Or if we add base, if we increase the hydroxide, the hydronium is going to go down. It's going to counter it. And so in other words, this is Le Chatelier's principle. Le Chatelier's principle says if I increase the product concentration, the equilibrium is going to shift left. That is, if I add more product here, it could be hydronium or hydroxide or both. It's going to shift it left, and then we'll establish a new equilibrium. And so we can look at some simple examples here. So this is a reaction, let's say, I don't know if it's uphill or downhill, but it doesn't really matter. If it's uphill, then K is small, very little product. If it's downhill, then K is large, lots of product. So uphill or downhill, we can know based on K. Once we have the equilibrium established, let's say it's downhill or uphill, once we have the equilibrium established, that is the population has stabilized, between the ones at the bottom of the hill and the ones at the top of the hill, then we might perturb that. And so once this has been established, we might add more H2S. If we add more H2S, we are adding more reactant and increasing the population down here. If we increase the population down here, that's going to mean that more molecules will make it to the top. And so, in other words, that's going to shift this to the right, if it's uphill. If we increase H2, that's product. So if we increase the population of product, it's going to shift it left. And so we call these shifts Le Chatelier shift. So if we increase the population of the reactant, it shifts it to the right. If we increase the population or the concentration of the products, it shifts to the left. So that's what they're saying here. Increase the H2S, we're going to have the 4 counteracting partially the increase in H2S by consuming some of it. So we'll get more 4 reaction. If we increase the H2, we're going to get a reverse. It's going to drop down to the other side as we get more product. All right, I guess we're out of time here, so we'll stop here. We'll look at more of the Chateliers. Unfortunately, the situation with the equilibrium is we really have to go into it in a lot of depth in order to do these calculations, which are at the end of this. And these are Chem 1B, topic of Chem 1B, so I'm not really going to get into it too much. We'll just do some simple stuff.